Hello everybody, welcome to another video lesson. Today we're taking a look at normal distributions. We're going to be able to use the empirical rule to analyze normally distributed variables and apply the standard normal distribution to z values to help us calculate some probabilities. So let's hop into it. All right, first off, what is a normal distribution? Well, it's kind of like what we looked at with a symmetrical distribution in previous lessons, where we have this nice bell curve. So a normal distribution is kind of that bell curve that we overlay over those symmetric histograms. It's a continuous symmetric bell-shaped distribution of a random variable. Now, we're going to be talking about standard deviation quite a bit today, so just a little reminder of what that is. That's just a measure that tells us how dispersed or how spread out the data is with respect to the mean. So is the data all over the place with respect to the mean, or is it really condensed with respect to the mean and it doesn't really deviate a whole lot? So that's really what our standard deviation tells us. Now our curve, like I said earlier, is continuous bell-shaped and symmetric with respect to the mean, which means that our mean, median, and mode are all going to be located at the center and they're all going to be equal to each other. Now our curve is going to approach but never actually touch the horizontal axis. So always remember that when you're sketching it out. And our total area under the curve is going to be equal to 1 or 100%. Now our empirical rule is one that is very important to us in this unit. It is showing, so this is the curve that we're talking about, our normal distribution curve, nice bell shape here. And right here in the middle, we've got our mean, okay? And then all of our sigmas that we see here are our standard deviations. So what our empirical rule says is that within one standard deviation of the mean, 68% of our data is going to fall within that interval. So if I subtract one standard deviation right here, it's subtracting one standard deviation, and then if I add one standard deviation that's right here, 68% of our data is going to fall within that interval. And then if I move out one more standard deviation on each side, so if I move out to 2 standard deviations here and here, then that means that 95% of our data is going to fall within that interval. And then going out one more time to 3 standard deviations, we have 99.7% of our data that falls within that interval. So basically all of our data falls within 3 standard deviations of our mean, which is important to know. Now let's take a look at what we call the standard normal distribution and z values. So combining these two is going to allow us to calculate a lot of probabilities. So our z values represent the number of standard deviations that any given data point is from the mean. Okay, so and we find this with a simple formula here. Z is equal to x minus mu over sigma, where x is our data value, mu is of course our mean, and sigma is our standard deviation. Now we need to combine this z value with this concept of our standard normal distribution, which again is just going to be this normal curve. However, our mean is 0. Our mean is 0 in this instance, and our standard deviation is 1. So you can see down here we have this mean of 0, and as I move, it's just 1, 2, and 3. That's because it's not 1 sigma that we're moving. Sigma is actually 1, so we're just adding 1, 2, or 3 because my standard deviation is 1. Now, this is going to allow us to assign actual areas under the curve to intervals created by our z values. So if we calculate some z values for a data set, even if the mean is not 0, okay, and oftentimes it's not going to be, but if I calculate the z values for certain data points within my data set, and say I have a z value that's like, say, I don't know, say this is 0.7 or 0.8 maybe, I can use that z value to calculate the area under the curve from my mean, and that's going to help me develop the probability of a data point falling within this area, okay, or within this interval. All right, so an example of this, the area between z is 0 and z is 1 is, we know this whole area, just extending this a little bit more, we know this whole area is 0.34. Therefore, the probability of a z value being in this interval is going to be 34%, because we know that the area under my entire curve is 1 or 100%. So let's use this and hop into some examples here. A normal distribution has a mean of 8.2 and a standard deviation of 1.3. Find the range of values that represent the middle 95% of the distribution, and then we're going to find what percent of data will be less than 4.3. So our mu, or our mean, is going to be 8.2, and our sigma value, or our standard deviation, is 1.3. So if I were to sketch out my curve here, this is a pretty bad curve, but that's okay, it'll work for our purposes. If I go one standard deviation in each direction, I'm going to start at 8.2, and then I'm going to add 1 sigma, which means I'm going to add 1.3, and that's going to give me a value of 9.5. And I'm also going to subtract 1 sigma, which gives me a value of 6.9. And we can do this for 2 and 3 sigma as well. So if I add 2 sigma, I get 10.8, and if I subtract 2 sigma from 8.2, I get 5.6. And then going on to 3 sigma, that's going to give me intervals of 4.3 and 12.1. Now remember, our empirical rule says that between the values of 1 sigma, that's where 68% of my data is going to lie. And then the interval for 2 sigma is where 95% of my data will lie, and 3 sigma is where 99.7% of my data will lie. So to answer part A, find the range of values that represent the middle 95% of the distribution. Well, I know that that is from 5.6 to 10.8. Now let's try to find B, what percent of the data will be less than 4.3. So I know that after 3 sigma, I only have 0.3% of my data set left, right? Only 0.3%, because 99.7% is going to fall within that 3 sigma interval. So since this is symmetrical, I know that if going one way past 3 sigma is going to be half of that 0.3%, or 0.15%, then going the other way past negative 3 sigma is again going to give me the same 0.15%. So to answer part B, the percent of data that will be less than 4.3 is 0.15%. All right, let's use our z values now. We're going to find x, which is our data value, if mu, or the mean, is 39% and sigma is 8.2. Not 39%, but just 39, and sigma is 8.2. And z is going to be, my z value is 0.73. Indicate the position of x in the distribution. So first thing, we're going to start off with our formula for z, and then I'm just going to plug in the values that I know, and that's going to allow me to find x. So first thing, I need to multiply both sides by 8.2, and that is going to cancel these two out. And then I'll add 39 to both sides, which gives me an x value of approximately 45. Now, how do I indicate the position of x in the distribution? So we need to sketch out a bell curve, our normal distribution curve, with a mean at 39. Now, 45 is greater than 39, so it's going to be on the right-hand side of 39, somewhere right about there. And how do I indicate where this falls as far as the z value goes? Well, I know that the z value tells me how far from the mean my data point is, my x value is. So I know that z was 0.73, so I know that 45 is 0.73 sigma away from 39, which was our mean. All right, last example here, finding probabilities. We have the lifespan of a certain tread of a tire are normally distributed with a mean of 31,066 miles and a standard deviation of 1,644 miles. Find the indicated probability, then use a graphing calculator to sketch the corresponding area under the curve. So we need to find our z values for each of these values within my probability. Okay, so first things first, let's find these z values by just plugging in 30,000 and 32,000. And we're going to find a z1 value of approximately negative 0.6484 and a second z value of 0.5681. So my z values are going to give me this interval in between both of these two that I just found. So now we can break out our graphing calculator and find our probability. So when we're doing this, we need to set the window up first. So when we set our window up, I want my x minimum and maximum. You can do this two ways. It can either be -3 to 3 or -4 to 4, but you don't need anything greater than that because I'm looking at a normal distribution. and your x scale should be 1, your y minimum should be 0, and your y maximum you could either put at 1 or 1/2. Either one of those should work for you. All right, so now you're going to go on your calculator, you're going to hit second vars, and you'll see above vars gives you the option, the second option is DISTR. Okay, so that's going to bring up your distribution page here, and you're going to scroll over to draw. Okay, scroll to the right until you hit draw, and the first option here is going to be shade normal. So when you click on that, shade normal, it's going to ask for upper and lower bounds. So your lower bound is going to be this first lower z value that you found, and your upper bound is going to be this second or greater z value that you found. And you just want to click through until, so you keep the mean at 0 and the standard deviation at 1, and then you click through and hit enter when you hit draw, and that's going to give you this nice bell curve right here. Now, when we're reading this, we can see that this gives me the area under the curve from my two z values. So from a z value of negative 0.6484 to 0.5681, it's going to give me the area under that curve. And that area is going to tell me the probability that we're actually looking for. That area is the probability that a certain tire has a lifespan in between 30,000 and 32,000 miles. So that probability is just the area that is already calculated for us right here, and that's going to be approximately 0.457. All right, guys, that is it for this video. Good luck with your practice.